Hello everyone. In this lecture we're going to look into some exceptions to the common rules that we use for nodal analysis and also find a workaround so that it makes it work, but also show you that if you go back and resort to the universal approach you wouldn't even deal with an issue like that. We will do the same thing for mesh analysis later on in the next lecture. So this is the circuit that we're going to analyze. If you recall, for nodal analysis, the process would start in the same way as we did before. For the universal approach, we first have to identify nodes. So this would be one of our nodes. This is the other node, one other node, and finally another node. So we have 1, 2, 3, 4 nodes for this circuit to consider. I'm going to pick my ground or my reference voltage. At that point, this voltage right here is going to automatically become a 50 volt once you write the equation for the component. So I'm not going to call it or introduce any other new variable. I'm just going to call it 50 volts. This node, I'm going to call that V1, and finally that node I'm going to call it V2. So that concludes all the nodes that I have to write equations for. So with nodal analysis, we said we're going to find the nodes where the value for the node is unknown. So out of these 4, it would be this node V1 and V2 that we would normally write the nodal equations for. And what more we said is that for each node, we no longer define currents for components in the circuit, and instead we're going to go to those nodes and assume there are currents that are leaving each node. Basically, for each node, the assumption is that there are currents leaving those nodes. And then we write the equations for those currents and add them up and equate them to 0. Since all the currents are leaving that node, the total current leaving one node has to be equal to the currents going into the node. And since there's no current going in, that's our assumption, then the total currents leaving that node would be equal to 0. So we start with V1 and try to implement that for the nodal approach. So keep in mind, that's our universal. So nodal. For node V1, there's current going this way, and that way. That's our assumption. For the current going through 5 ohm, the equation for that current is a simple ohm law. So that would be V1 minus 50 divided by 5. We add that to the current going through the 50 ohm, which again is another ohm law, would be V1 minus 0 divided by 50. And then we get to the current that is going through that source. This is a dependent source, right? With this symbol, we know that this is a dependent source. So what does that mean? That means that the voltage across this, meaning the voltage of the potential of the positive terminal minus the potential of the negative terminal, is this function, which is a function of another parameter in the circuit. In this case is 10 times current I1 being the current that is passing through the 5 ohm in that specific fashion. So let me actually tell you something at this point that is sometimes a source of confusion. Even though that this equation is a function of current, this value is actually a voltage across this source, because this is a voltage source, right? So sometimes people assume, since this is an equation that has currents in it, this is actually defining the current that is passing through that component, which is inaccurate. It's actually incorrect. The equation for that dependent source is that the potential of the positive terminal, which is V2, minus potential of the negative terminal, which is V1 in this case, is equal to 10I. So I'm going to write that down here. So we know V2 minus V1 is equal to 10I1. That is the equation for that component. Now, when it comes to writing the nodal analysis, I need to know what the current going through that component is, because I'm assuming there are currents leaving node V1, and then when it gets to this current leaving V1 through the dependent source, I actually don't have any equation that defines that current. It's not like any other of the Ohm laws that we wrote. So this becomes basically a question mark that I don't know how to write an equation for. Therefore, this specific situation, if you ever get to a situation like this, and in this case, this happened to be a dependent source. This could be an independent source, and you would have the same issue here. If you get to this situation, here's the workaround. So what you can do, since you don't know what the current going through the source is to define a new node that includes the source so that you don't have to then deal with the current that is passing through it. So let me put this new node, basically. That includes both nodes of V1 and V2. Okay? So now, with nodes, we said as long as we put a sphere or circle on a piece of paper, and there is no source or sink of electrons inside that closed area, then all the currents or all the electrons going in has to be equal to the electrons going out, or all the currents going in has to be equal to the currents going out. And since within this there is no source that generates electrons and no sink that through which the electrons can disappear, for this new enclosed area, still I can write a KCL, meaning that I can assume now currents are leaving that new closed area or new node, and then finish this equation for that node as opposed to the node to the left. So now this node, sometimes in books, is called a supernode. It's a node that includes more than one node, right? And therefore it's going to include some components. And the motivation is that by putting the node like so, I have included the source inside, or this component inside the node, and therefore no longer I need to write an equation for that current. So let's actually now write the nodal equation for this new supernode and see what happens. Okay, so the equation for the current passing through the 5 ohm would still be the same. So V1, this is for supernode, minus 50 divided by 5 plus the equation through 50 ohm would be still the same, V1 divided by 50. Now there is current going through the 100 ohm coming out of that same node, same supernode, and that equation would be V2 minus 0 divided by 100. And then finally there's the current leaving that node through this path, to which there's a current source connected to, which means there's current 4 amp going in, and if I'm assuming for the sake of this analysis that there is a current leaving that node, that current has to be minus the value of the current that is going in. And then the whole thing is equal to 0. It's the same thing as saying these currents are leaving equal to the current going in, but we're just going to stick to that general form. Okay, so now I have one equation for that supernode, but this one equation obviously is not enough, because at this point I have 2 unknowns and 1 equation, so I need more equations. So the second equation that I immediately can use is that V2 minus V1 is actually equal to 10I1, the equation for that component inside. So there is another equation, V2 minus V1 equal to 10I1, that I can use. Now this equation adds one more equation, but also adds one more unknown. Therefore I have to actually use the equation for I1 here, which defined as V1 minus 50 divided by 5 ohm, which you already had it there. So if I put this here, then I get, so let me do that. So V2 minus V1 is 10 times that equation, which means it's equal to 2 times V1 minus 50. So with that, I get this equation that relates V1 and V2 to each other, that equation that relates V1, V2 to each other, and basically now I can solve this set of equation and calculate voltages V1 and V2, at which point then if I need to go back and calculate all the rest of the currents, I just use the Ohm law for those. And that concludes the nodal analysis for this specific circuit. Now, keep in mind that I had to deal with an exception, define a new concept, supernode, but at the end of the day, you can actually manage to solve it once you use those. Let's go back to our beloved universal approach. Now, labeling the circuit would be the same. So we label the circuit. We're going to use the same labels. But next, we're going to actually label the currents passing through components. Notice that one of these currents, since it's used for defining what the voltage of the dependent source is, it's a given, and you're not supposed to change that definition, because if you change that, then you have to go and change that equation at the same time. Okay? So we're going to leave that alone. For the source, I'm going to assume there's a current going down, and I'm going to use KCL for that node and call it I1. Now, you may say, well, we usually assume that the current is leaving the positive terminal of the source. Why are you assuming that it's going down? I just did that because the current was going into that node, and once I assume the current is going down, these two currents become exactly the same. If I assume this current is going up, then I have to define it as minus I1. It's the same thing, but it's just easier to deal with it this way. Now, again, the direction of the current that I assume here is completely arbitrary. I'm not actually saying the current is going to end up going down in this branch. I'm just making an assumption, and then I'm going to calculate all the currents and voltages. Once I have the actual value for I1, if that value ends up being a negative number, it means that the current is actually going the other way around. That's the point that the actual direction of the current is going to be determined. Not at this point. This is completely arbitrary, so you can pick any direction you want. And for simplicity, I assume that it's going down. I'm going to do the same here, call that I2. Here, call this I3. This one, obviously, is 4 amp. That's the definition for, or the equation for that component. And finally, I'm going to actually assume a current going through the source too, right? Each component has a current passing through it. I'm going to call that I4. And that concludes the definition of all the currents and voltages for this circuit. So again, we're doing this now, not nodal analysis. So we move on to KCL and equations for components. In order to write KCL, I look at my nodes. I have 1, 2, 3, 4 nodes. To this node, we don't have to write a KCL for. This one, we already wrote a KCL for it. So these are the only two KCL equations that are left to do. So KCL. For node V1, I1 and I2 are leaving that current. Actually, I4 is also leaving that node. So it becomes I1 plus I2 plus I4 is equal to 0. And then for node V2, I4 and 4 amp are going into that node, and I3 is leaving. So I3 is equal to 4 plus I4. That concludes my KCL equations. I'm going to move on to equations for components. Now, again, I count the number of components I have. 1, 2, 3, 4, 5, 6. 2 of these components, I already wrote the equation for them when I was defining the voltage, node voltage here, and the current for that branch. So I don't have to write equations for those 2. There are 4 equations left to do. For the equation corresponding 5 ohm, I have I1 is equal to V1 minus 50 divided by 5. For I2, I have V1 divided by 50 ohm. For I3, I have V2 divided by 100 ohm. Let me rewrite this one. Actually, let me write it here. So I3 would be V2 divided by 100 ohm. And finally, the equation for the dependent source, which is this equation, is V2 minus V1 is equal to 10 I1. Okay, so let's now count the number of unknowns in the circuit. We have I1, I2, I3, and I4 as unknown, and V1 and V2 an unknown. A total of 6 unknown. Let's count the number of equations. 1, 2, 3, 4, 5, 6 equations, 6 unknowns. This is a solvable set of equations that gives us values for all the unknowns in the circuit. So now notice that following up the same principal concepts that we already had, we did not have to do any new definition. There was no need to do a super node at that point. We just followed the same rules and got it. So no exception when you go back to the original universal approach. Whereas if you wanted to do nodal analysis, you had to do the super node. And if you're comfortable doing that, more power to you. Just use that. Keep in mind, this is going to end up, at the end of the day, it's going to only give you V1 and V2. If you're looking for currents, then you have to do more. Whereas when you do this and you finish, you already have all the values for the circuit components. Now, there's one more thing that I want to mention before we finish, and that's the fact that if you notice this equation right here, if I move, so I1 plus I2 plus I4 is equal to 0, right? So if I take I4, the equation for I4 from here, so from this equation, I know I4 is equal to I3 minus 4. Now I take this and put it back to in that equation. So using this, I'm going to rewrite that equation. That would be I1 plus I2 plus I3 minus 4 is equal to 0. Now notice this. This equation is actually exactly the same as that equation that we wrote for the supernode. So it's as if writing the equation for a supernode is equivalent to writing 2 KCLs for those 2 nodes inside and then combining them to each other. It's the same thing. It's like you're starting with this and then combining the 2 to get one equation. And with that, what we really mathematically did was to get rid of I4, which we didn't know how to write an equation for, right? So this is basically the same as saying this is a mathematical trick. You write the KCL for those 2 nodes, combine them, then you get rid of I4, and then you don't have to have an equation for it. Now, which one you prefer? You want to write the whole thing like that and then do the combination, or you're comfortable doing a supernode? It's completely up to you. I'm more comfortable following one algorithm and let the math take care of the rest. At this point, I'm going to stop this lecture. We're going to move on to the next lecture where I'm going to show you exceptions to the common rules that we explained for mesh analysis. Thank you.